All right, well, first we're going to convert between Kp and Kc because sometimes we will need to do that for our equilibrium problems. So this is the equation that Kp equals Kc times the gas cell constant times temperature time to the delta N. So this R, for some reason, is out. Okay, so it's Kp equals Kc times RT to the delta N. And delta N is moles of gaseous products minus moles of gaseous reactants. And R is the gas cell constant 0.0821 liter atmospheres per mole Kelvin, so temperature has to be in Kelvin. If we needed to change that around to solve for Kc, it would be Kp over RT to the delta N equals Kc. Okay, so we can find Kp if we know Kc, or we can find Kc if we know Kp. Okay, so example problem. Calculate Kp for the following reaction. PCl3 plus Cl2 gas goes to PCl5 gas, and the Kc is given. It's 1.67 at 500 Kelvin. Remember, K changes with temperature. So at 500 Kelvin, the Kc is 1.67. So now to calculate the Kp, we need to know what the delta N is. Well, there's 1 mole of gaseous product, and there's 2 moles of gaseous reactant. So 1 minus 2 is -1. So delta N is -1. So again, looking at the formula, Kp equals Kc times RT to the -1. Kc is 1.67. And then the K, or the R, and the temperature were to the -1, so that's the same thing as putting them on the bottom. And so dividing that out, it's 0.0407 is the Kp when the Kc was 1.67. Okay, another example, a chemical engineer injects limestone, calcium carbonate into a hot flue gas of a coal-burning power plant to form lime, which scrubs SO2 from the gas and forms calcium sulfate. This is important for pollution control because SO2 contributes to acid rain. So they have the scrubber in there, and the reaction is that calcium carbonate solid forms calcium oxide solid plus CO2 gas, and the reactant is a solid, one of the products is a solid, and then we only have one product that's a gas. So this is a pressure for a gas. So our Kp would just be equal to the pressure of CO2. Normally, remember, K is products over reactants, but we only have a concentration for or a changing amount for gases and aqueous. So solids do not get put into the K expression. So it's just Kp equals the pressure of CO2. And we have that Kp, it's 2.1 times 10 to the -4th at 1,000 Kelvin. We want to convert the Kc. So once again, looking at delta N, we have 1 mole of product gas and no moles of reactant gas, so it's just 1. So it'll just be Kp is equal to Kc times RT to the first. Rearranging that to solve for Kc, we divide over the RT, and we get Kc equals Kp over RT. So plugging in Kp, 2.1 times 10 to the -4th, plugging in R, 0.0821, plugging in the temperature in Kelvin, which is 1,000, we solve for the Kc, 2.6 times 10 to the -6. So with this equation, when would Kp equal Kc? Well, since it's to the delta N times RT, if delta N was 0, then that RT term would just be 1. So Kp would equal Kc when the RT term is 1 because the change in N is 0. So that means if the moles of gaseous reactants equals the moles of gaseous products, then that's when Kp would equal Kc. Okay, so when the moles of gaseous products equals the moles of gaseous reactants. That's when they would equal each other. Okay, so that's converting Kp to Kc. Now we're going to go into solving ice problems, equilibrium problems where we are either finding the K from the concentrations of the reactants and products or finding a concentration at equilibrium when we have the K or things like that. So we're going to skip over to ice problems. So ice problems, ice stands for initial concentration for the I, change in concentration for the C, and equilibrium concentration for the E, okay, ice. So in this type of problem, we're always going to set up that little chart, and we need to write it underneath our balanced equation. So we have PCl5, and you already can see up at the top what the states are. You don't have to rewrite them as long as you understand that when it's a pure liquid or a pure solid, they will not have an amount. They won't have a concentration that's changing. Okay, so I guess we can just go ahead and write the gas in so that we actually have those. All right, so ice. Initial. Do we have the initial concentration? Well, we have moles. It says at a certain temperature in a 1 liter flask initially contained 0.298 moles of PCl5 and 8.7 times 10 to the third moles of PCl3. So since it's a 1 liter flask, molarity we know equals moles over liters. So it will just be the moles over 1. So in this case, the molarity will be the moles. But if it's not a 1 liter flask, if it's a 2 liter flask or a 3 liter flask or whatever, you have to do that division. You have to put in molarity into the ice chart. Okay, it needs to be molarity, not moles. So what do we have? We have 0.298 moles of PCl5. So 0.298 molar, since it's 1 liter. And we have 8.7 times 10 to the minus third molar PCl3. And then it says after the system reached equilibrium, then that's how much Cl2. So we have no Cl2 given to begin with, so we must not have any originally. Okay, change is what the C is for. So C is change. Well, when you have something that has no amount, we know the reaction is going to go that way, okay? Because this is 0, the reaction to reach equilibrium will have to go towards the products to produce some Cl2. Okay? So because that one is 0, we know the reaction is going this way. And we also know that, so this is going to lose some amount since the reaction is going to make products. And this is going to gain some amount because more products are being formed. The X's have to match up with the mole ratios. So there's 1 mole of PCl5, so it's minus 1X or X. If it was 2 PCl5, then I would have put minus 2X. Okay, so the X's are losing when it's going this way to the right. So the product's going to lose some, the reactants are going to gain some, and we look at the mole ratio to see if it's a 1X or a 2X or whatever. Okay, so these were all 1s in the balanced equation, so it's minus X plus X plus X. The other piece of information given is that at equilibrium, 2.00 times 10 to the minus 3 moles of Cl2 was formed. So again, we can make that a molarity because it's 1 liter. So we're dividing. All right. So that's what we have so far for our ice chart. Now, I and C have to equal E. So they add together to make E. So we don't know what, we weren't given the equilibrium amount of PCl5, but we know that it'll be 0.298 minus X. Okay, so those two add up to that. Same thing with this one. We don't know what it is, but we know it was 0.87 times 10 to the minus third, and then we're going to add X amount to that. But then we do know the concentration in this one of the Cl2 at equilibrium. And now if we look at what this was, it was 0 plus X equals 2 times 10 to the minus third. So that means that X equals 2 times 10 to the minus third. And we can go back in now and plug in that X here. So this will be plus 2 times 10 to the minus third. And this will be minus 2 times 10 to the minus third. Okay, so in this one, we were able to solve for X. The change in the amount of Cl2 was the equilibrium concentration of Cl2 since we started with 0 of it. All of that had to be the change if that's what the concentration was at equilibrium. All right, so then on our calculator, plugging in 2.98 minus 2 times 10 to the minus third, that will be, it's 0.298 minus 2 times 10 to the minus third, and that is going to be 0.296 is that new concentration, and this one is 8.7 times 10 to the minus third plus 2 times 10 to the minus third. So that one is 0.0107, and then this one is already 2 times 10 to the minus third. So we have the amounts of the three things. The question said, calculate the equilibrium concentration of all species. So we just did that. And it says calculate K. So K will be equal to products over reactants. So the concentration of Cl2 times the concentration of PCl3 over the concentration of PCl5. We now have all those amounts. So it's 0.0107 times 2 times 10 to the minus third divided by 0.296. So that is equal to 7.23 times 10 to the minus fifth. So that equals K, okay, or KC, if you want to call it that. All right, so that's one example of we were given some of the information to plug into the ICE chart. We could figure out what was missing, and then we can calculate K. Let's try another one. Okay, a mixture of 5 times 10 to the minus third moles of H2 and 1 times 10 to the minus second moles of I2 is placed in a 5-liter container and allowed to come to equilibrium. All right, so our balanced equation wasn't given. So writing that, we know we have H2 plus I2 is placed into a container, and that's going to form HI, and it will have to be 2 of them. Okay, and we're given just the amounts of those 2, but we're given that it's a 5-liter container. So we need to take that 5 times 10 to the minus third and divide it by 5 liters. So that makes 1 times 10 to the minus third for the initial concentration of H2. And then for the other one, it's 1 times 10 to the minus second, and we need to divide that by the 5 liters. Okay, so 1 times 10 to the minus second divided by 5 is 0.002 molar for the I2. All right, again, this has to be in our ICE chart. It has to be in molarity, not moles. So plugging in H2, it was 1 times 10 to the minus third. Plugging in I2, it was 0.002. Okay, and we are not given any HI to begin with, so that is 0. So once again, we know that if this product is 0, that the reaction is going that way. So this will be losing X amount, this will be losing X amount, but this will be gaining twice as much. It'll be gaining 2X, okay, because there's a 2 in front of the HI. So now, when we have this, this will be 1 times 10 to the minus third minus X. This will be 0.002 minus X, and this will be 2X. Okay, so it tells us to also that the concentration of HI is 1.87 times 10 to the minus third at equilibrium. Okay, so actually right here, okay, I can plug in the 1.87 times 10 to the minus third. Now, once again, same type of problem as the last one. I know that 2X has to equal that number. So 2X has to equal 1.87 times 10 to the minus third, because I started with 0 amount and I ended at that. So 1.87 times 10 to the minus third divided by 2. So then X is 9.35 times 10 to the minus fourth. Okay, now I can go back and plug that in. I can subtract that here, so 0.002 minus 9.35 times 10 to the minus fourth. Is 0.001065 molar. And same thing here, I can take 1 times 10 to the minus third minus 9.35 times 10 to the minus fourth. 1 times 10 to the minus third minus 9.35 times 10 to the minus fourth. And that equals I think I did something wrong. 1 times 10 to the minus third minus 9.35 times 10 to the minus fourth equals, yep, that's right. 6.5 times 10 to the minus fifth. All right, a little messy. So now I have all the concentrations and it says calculate Kc. Okay, so plugging those amounts into the K expression. What is the K expression? It will be HI squared, because there's 2 HI, over concentration of H2 times concentration of I2. So plugging those in, it is 1.87 times 10 to the minus third squared over 6.5 times 10 to the minus fifth times 0.001065. Okay, so that's going to be 7 times 10 to the minus third squared divided by 6.5 times 10 to the minus fifth and that equals 50.5 for the K. And there are no units on K. Okay, so just 50.5. All right, so that's two examples where it was pretty easy to figure out what X was because we didn't have the amount. Initially, we had nothing, and then at equilibrium, we were given an amount. All right, but all problems aren't going to be like that. So this problem is a little different. This one, you have H2 plus F2, and it's making HF, and it's given you amounts of everything to begin with. So it says in a particular experiment, 3 moles of each component was added to a 1.5 liter flask. Calculate the equilibrium concentrations of all species. Not really sure why all of these are off by. Sorry, my paragraphs are off for some reason, but that's okay. We'll just ignore that. All right, so we have our ice set up. All right, so the equilibrium constant was given in this one. So we have K. We also have 3 moles of each added to a 1.5 liter flask. So calculating the equilibrium concentration of all species. So at the beginning, we have 3 moles of each in a 1.5 liter flask. So we have 2 molar of each thing. Now, when you start with amounts of everything, you have to figure out which way a reversible reaction is going to go. In the first two we just looked at, the product was 0. So we knew it was going to go towards reactants. But in this case, we have amounts of everything present. So this is where Q comes in. Remember, Q is the reaction quotient. And Q, if it's equal to K, we know it's at equilibrium. If it's less than K, then we know it has to shift to make more products. If it's more than K, then it has to shift to make more reactants. So separately, off to the side, we're plugging in. We have 2, so Q is with the initial amounts. So we have 2 molar of HF, we have 2 molar of H2, and 2 molar of F2. So plugging that in, 2 squared over 2 squared equals 1. So Q equals 1, but in the problem, they gave us K, and it was 115. So Q is less than K, so we need more product. So then we know the reaction is going to go this way. Okay. So we know it's going to go this way. So now we know we're going to lose X amount of this, we're going to lose X amount of this, and we're going to gain 2X, because there's a 2, we're going to gain 2X of this. Okay. So then this will just be 2 minus X, this will be 2 minus X, and this will be 2 plus 2X. So in this one, we were not given any information about the amount at equilibrium. So this is going to be, we're going to have to do the math problem to solve for this without any equilibrium information given. So still plugging in products over reactants, and then coefficients are squared in the equation. So just like the Q, the K will be the concentration of HF squared. So that's 2 plus 2X squared over 2 minus X for the H2 and 2 minus X for the F2. And then we do know that that equals 115. So in this particular problem, solving for X, it could be where we would have to do a quadratic equation. But if we look carefully, we can see that the top is squared and the bottom, if we multiply those two together, those would be squared. So we actually have a perfect square on this side. This squared over that squared equals that. So we can take the square root of both sides in this problem, and it'll just be 2 plus 2X over 2 minus X equals the square root of 15. Okay, so then now when we plug that in, then we can multiply over the 2 minus X, and we can solve for x. Okay, so this one, we don't have to do the quadratic. We can just solve mathematically. So the square root of 115 is 10.724, multiplying over the 2 minus x, and then distributing that, and then combining like terms and all that. We come up with a value of x is equal to 1.53. Okay, so that was much easier than having to do the quadratic. But if it weren't a square root on both sides of that, and we had an x squared term and an x term, then we would have to do the quadratic. But we're going to save that for another day. So as of right now, you're going to have to set up some ICE problems where you will either be given an amount at equilibrium so that you can solve for x, or it would be like this where you have a square, a perfect square on both sides that you could, or on the one side, that'll both be squared and you can solve for x. All right, so we're going to now try some ICE problems.